Day one of non-traditional instruction had its ups and downs, but yesterday the video I recorded did not work, so we're going to take a look at this example to help out those people who missed it. When we're dealing with solution stoichiometry, we're doing stoichiometry again, and the idea is we've got to have moles. So instead of starting with moles or starting with grams, we're starting with a volume and a concentration, and our goal is to get moles. So that's nothing new. In fact, almost the entire problem is old stuff. There's just a tiny bit of new stuff. In fact, one of the first new things is we're going to have trying to figure out how to get moles. And then the other new thing we're going to have is at the end. So what I want to do is preemptively indicate this is going to be something that is new. And then I'll indicate where the new stuff's going to show up. And I wrote this problem out in advance to save some writing. Since it is stoichiometry, the skeleton of the problem is familiar information. I'm going to have to do something new right there. And I'm going to have to do something new right here. In fact, I'll just box this in. Everything else on these pages is, for all practical purposes, old stuff. And I will be putting in a little bit of new information right here, and a new bit of information right here. But that'll just be supplemental to the type of stuff we've done before. So preemptively, we've gone through and labeled where the new things are going to be. The only new concept we have to add here for solution stoichiometry is molarity. And we know from some of the previous videos or previous work that molarity is moles of the solute over the volume in liters of the solution. Now in this particular case, we're given molarity and we're given volumes, and so we can get moles. And so I'll rearrange this where moles is the molarity times the volume in liters. Okay? Super duper important. This is what we're going to use to do this first step right here, turning our volume and concentration into moles. So that is what I'm going to do right there. We know that moles is going to be our molarity times our volume in liters. My molarities are right here, and my volume in liters are right there. And so those are the numbers I'm going to carry over. We have 0.20, and that is times 0.250 liters. And we have 0.20 again, but this time it is 0.400 liters. And again, those numbers were given. I did a quick conversion of milliliters to liters, but those molarities stayed as they are. When we plug these numbers in, we end up with 0.050 moles of the lead nitrate and 0.080 moles of the Ki. And this is a standard stoichiometry setup where you've got what you have in moles. You've got these ratios from the balanced chemical equation, and then we're just finding this out over here. So 0.05 times 2, we get 0.10 moles of the Ki that we need, and we get 0.040 moles of the lead nitrate that we need. A quick glance at that shows you that our limiting reactant, the one we don't have enough of, is the Ki. You have 0.08 and you need 0.10. So this is our limiting reactant, and this is our excess reactant. Again, everything I'm doing right now is old news, all right? That. If you see me writing something in those orange boxes, that's the new stuff. To get our amount excess, there's no new type of calculation there. We have our excess reactant, 0.050 moles that we have, and 0.040 moles that we need, which gives you 0.010 moles of the lead nitrate excess. Nothing new, right? That's all stuff that we have done before. So I'm going to continue on. Generally, we find our theoretical yield using our limiting reactant, and that's what we're going to do right there, and I've already kind of set that up for us. Our limiting reactant was the potassium iodide. We have 0.08 moles of that, and that's what I'll pick up with right here. We multiply by 1 and divide by 2. I'm taking care of both of my products here, the lead iodide and the potassium nitrate. So we end up with 0.040, that's 0.08 times 1 divided by 2. And 0.08 times 2 divided by 2 is 0.080 moles of KNO3. Again, nothing new up to that point. We're going to add in one calculation. We have moles of lead iodide. In the original problem, we were given an actual yield. And so I'm going to carry that number over. In fact, maybe I can highlight it a little bit. This number is going to carry over to right there. All right. Now, that was 14 grams, and I'm going to need to get grams of our lead iodide. We are told that it's lead iodide. But first, let's write our 14 grams of lead iodide. And we're going to divide by our theoretical yield. We have moles there. We need grams to make it match. We could turn these grams into moles, or I could multiply by the molar mass and get grams up here. And I happen to have calculated that. It is 461 grams per mole, giving us a theoretical yield of 18 grams PbI2. All right, so this is our actual yield, and that's what I'm going to put in right here, 18 grams. So we have 14 over 18 times 100. That is a 78% yield. And let's take a look at our original prompt to see what information we've completed. Did we identify the limiting and excess reaction? Yes, we did. Okay. In fact, let me try and sneak this on the page at once. So we've done that. That's part A. Have we gotten the amount excess in moles? Yes, we did. It's right there. This is our part B. Did we get a theoretical yield in moles? Yes, those are those numbers right there. That's our part C. Did we get a percent yield? We did. That is part D. Everything we've done for all of those, A, B, C, and D, is stuff we've done before for stoichiometry problems. And now we need to take care of part E, which is new stuff, right? We had said for solution stoichiometry, it's going to be basically the same. New step at the beginning. We did that. We just had to take a volume and a concentration and turn it into moles. And then a new step at the end, and that's what we're going to need to take care of there. If we're going to find the concentration of species present in the final solution, we need to know what's going to be in the final solution. And in a previous video, I established that there's only two things you're looking for. And that was this video right here. And the two things we end up looking for, our aqueous product, those are spectator ions, and our excess reactant, because that is what is left over. So this is our template of what we're looking for. And we can tie that back to how double replacement reactions work. This is our page 2 back. I've written out the double replacement reaction. We had to have that for stoichiometry. And I'm going to fill in some phases. Lead nitrate, we follow these solubility rules that we've seen before. Lead nitrate is aqueous because nitrate compounds are generally aqueous. Potassium iodide ends up being aqueous because group 1 metal compounds tend to be soluble. Or bromides, chlorides, and iodides tend to be soluble unless they're with lead, silver, or mercury, which comes into play here. I have iodide. Initially, I would expect it to be soluble, but I've got lead there. So we do end up with a solid. It is insoluble. Group 1 metal, nitrate, we're going to end up aqueous. All right? So that's something we've done previously in our double replacement reactions, is use solubility to predict these. And we said that anything that is aqueous, we are going to dissociate. I've done that in advance to save us some writing. Let's just look at that real quickly. Lead ions and 2 nitrate ions. 2 potassium ions and 2 iodides. A common question I get is, do we need to put those charges in there? And the answer is yes. It's a life or death situation. Potassium, metal, would kill you. Potassium ions are necessary for your muscles to work. So the difference between showing that charge and not showing that charge is the difference between life and death. This is solid, it is insoluble. So that did not dissociate, but our potassium ions, we have 2 of those, and we also have 2 of our nitrate ions. When we were looking at the idea of spectator ions in double replacement reactions, when we were trying to get complete ionic equations and net ionic equations, we're going to look for the spectators that remain unchanged from reactants to products. So lead ions, I don't have lead ions on the product side. That's not a spectator. So that is involved in the actual chemical reaction. Nitrate ions, I do see nitrate ions over there. So this is going to be a spectator. And again, if it remained unchanged from reactants to products, it didn't change. So it's a spectator. It wasn't part of the reaction. Potassium ions, I've got those as well. That'll be a spectator. Iodide ions, I don't have those over there. They've changed into something else, so we end up with that. The actual reaction that took place was lead ions and iodide ions making lead iodide solid, which then precipitated out of the solution. And that is a super important bit of information, so let's take note of that. In the final solution, we don't have this, okay? This is a solid. It has precipitated out of the solution. It's insoluble. Therefore, it is not in the solution. It has precipitated out. So in terms of things that I'm not looking for in our final solution, I'm not looking for lead iodide. Now, under stoichiometrically equal conditions, this and this would both be used up. But in this particular case, I had an excess reactant. It was the lead nitrate. So I have lead ions and nitrate ions in my final solution. In fact, let's take note of that. Lead ions and nitrate ions are in the final solution. And why is that? Because there was some left over. All right, those were excess ions, and we got them in the final solution. As we look at the other side, we've already established that this is not in the final solution. I don't have these ions or these ions because they were consumed, so this right here is not in the final solution. Because it's used up. A more appropriate way to say that would be it is completely consumed. It's our limiting reactant. So I'm not going to be looking for that in my final solution. As you look over here, though, I do have these potassium ions and nitrate ions because they didn't change. They are spectators. So this is in the final solution, right? Because they are aqueous products. And that ties back into what we said earlier. We are expecting to see our excess reactant and our aqueous product in the final solution. Our aqueous product and our excess reactant. And that's what we have. So I know that part may seem complicated. If you want to just cut corners, skip to these orange boxes, this is my excess reactant. We've already established that that lead nitrate is going to give us lead ions and nitrate ions in the final solution. So let's figure out how many lead ions and how many nitrate ions we have in that final solution. And we can do that by a simple dissociation. For every one lead ion, or every one lead nitrate, I have one lead ion. So that's 0.010 moles of Pb2+. And for every one lead nitrate, I have 2 nitrate ions, so that's 0.020 moles of nitrate ions. So as we're looking at this excess stuff, lead ions, I've got 0.010 moles of. Nitrate ions, I've got 0.020 moles of, because that was left over when the reaction took place. And I'm going to put that in this orange box here. It's important information. 0.10 moles of lead ions and 0.020 moles of nitrate ions. All right, that is important information. This is from our excess. And I'll highlight that a little bit crosswise so we can come back to it. That is new information. That was a new step. And as we look here, we need some new information here. And that new information is based on our aqueous product. We said in our final solution, we're going to have potassium ions and nitrate ions, and they're going to come from that aqueous product. In our dissociation here, for every 1 potassium nitrate, we have 1 potassium, and for every 1 potassium nitrate, we have 1 nitrate. That's 0.080 moles of potassium ions and 0.080 moles of nitrate ions. And that stuff is coming from my aqueous product. And I'll highlight that that is in our final solution just so I can keep track of it. I want to catch up with a quick summary here before we get into this last step. It may feel overwhelming at this point, and once you get the hang of it, every single one's the same, so don't get super stressed. It's all stoichiometry. So we needed moles and a balanced chemical equation to do stoichiometry. The way we got our moles was to use molarity times the volume, and that happened right there. Then we entered the part where we had stoichiometry as we always did. We found our limiting and excess reactant. We got an amount excess. We got a theoretical yield, and we got a percent yield. That's all old information. And then we had to dissociate the aqueous product and the excess reactant. And we did that right here. That was a new step. Since this is excess, those ions are floating around in solution, so they are in my final solution. All right? Since this product is aqueous, these things are in my final solution. And we had predicted that when we looked at this complete balanced chemical equation. Since these weren't all used up, they would be present in the final solution. And since these were aqueous in the final product, then they would be floating around as ions in solution. And now we need to take care of this. We just listed out those species that are present in the final solution. We have to come up with some concentration of lead ions, some concentration of nitrate ions, and some concentration of potassium ions. And you'll notice it also says nitrate right there. We're going to have to take that into consideration when we're calculating this number. Now, I'm about to write something that isn't technically part of this problem, but I like to do it for easy bookkeeping. All right, so this isn't necessary, what I'm about to write, but for my own purposes, I like to keep track of where these things came from. So if you look, the lead ions came from our excess. And the nitrate ions also came from our excess, but from our aqueous product as well. The potassium ions came only from our aqueous product. All right, again, that's not a critical step, but for me, it's good bookkeeping, and anyone can look at this and see where I got these things from, right? And this is from our aqueous product. All right, that's what we have in the final solution, but now I need to know those concentrations. And you may recall concentration, we already mentioned, is going to be calculated as a molarity, which is moles of our solute over volume in liters of our solution. So let's write that equation. Our molarity is moles of our solute over the volume in liters of our solution. So each of these, we're going to have to do that calculation. And I've got things labeled so it's easy to find. Lead ions from my excess, from the excess, I have 0.010 moles. And that's the only place I need to look. Nitrate ions, I'm going to look at my excess, where I have 0.020 moles. And I'm going to look at my product, where I have 0.080 moles. And potassium ions, I'm going to look at my product, and I have 0.080 moles of that. And that leaves us with one final hurdle to overcome, and that final hurdle is, how do we get the volume of the solution? Okay? And the first time around, I think this is a really scary step, but once you've seen it once, I think it's no problem, and I'm going to flip back to the first page. The only volumes we have were those volumes that we were given in the original prompt. That is the 250 and the 400. And so how are we going to get a total volume? Let's see if this color shows up. To get a total volume, we better improvise. We're going to have to take the first volume plus the second volume. And we'll just call that V1 and V2. Doesn't really matter. Saying this is more work than it actually is. Add those up to get the total volume. So our volume total is going to be 250 milliliters and 250 milliliters. Sorry, 400 milliliters. That is 650 milliliters, aka 0.650 liters. And that is the volume we're going to need. Let me highlight that. These numbers are what we started with. The total volume, when we mix these two beakers together, is going to be the sum of those volumes. And that is what I'm going to put right here, and right here. We had 0.650, 0.650, and 0.650 liters. So again, in our final solution, our total volume was the sum of the original volumes, and I calculated that on the other page. Now we just need to write our answers. It seems like this has been a long time coming. 0.1 over 0.650 is going to end up 1.5 10 to the minus 2 molar lead ions. For our nitrate, we end up with 0.12 molar potassium ions. And for our potassium, oops, I wrote that backwards. 0.12 molar potassium ions and 0.154 molar nitrate ions. And that gets us this final answer, the concentration of our species present in the final solution. And as you may recall, that was our part E. All right, that is the entirety of that problem. I would tune out now if you're feeling a little overwhelmed by that, but I do want to mention something that's kind of interesting, and it's a little bit of a fail-safe you can do. Potassium ions, nitrate ions were spectators. In the beginning, I had a certain number of potassium ions, and I had a certain number of nitrate ions. In the end, I should have all of those, right? So for instance, in the beginning, my potassium ions, I had 0.080 moles of. In the end, I had 0.080 moles of potassium ions. All of it, right? So this is kind of a shortcut that people sometimes use, or at least a way that you can check things. In the beginning, I had 0.10 moles of those nitrate ions. I had to double it. So in the end, I should have had 0.10 moles of nitrate ions. And I had 0.02 from my excess, and I had 0.08 from my products. Add them together, and you get 0.05 times 2, 0.1 moles. So you might see people occasionally cutting corners and just saying, all right, all the nitrates I started with, that's 0.10. All the potassiums I started with, 0.080. it works fine, or it works as a way of checking things out.